Hello, AP Calculus. We're going to dive into our first lesson on calculus, which is about limits. And that might sound kind of foreign to you, but you have actually discussed limits without actually using that term. Now, before we dive into this, I'm going to pose a question that I'm actually going to have you answer at the end. And the question is, can change happen at an instant? All right, so we'll just leave that there for now. Have you stew on that for a minute. Okay, so things we're going to do, we're going to estimate a limit using a numerical or graphical approach. And we're going to learn all the different ways the limit can fail to exist. One thing I want to mention is that one of the main ideas in AP is that we want to make sure that we can justify our reasoning using kind of it's called the rule of four. So that would be verbally, numerically, graphically, and analytically. And analytically would be basically algebraically. So we're going to focus on numerically and graphically justifying our responses today. So this, as you see, is a starter, and normally I would have students do this on their own. So if you would take a minute, actually just maybe pause and consider this. So this should look very familiar to you. You have a function f of x. And these tables they come from the same function. They indicate some key features of the function. This should look familiar because you did this very problem in honors pre-calculus. So pause for a minute, see what conclusions you can make about these tables. Okay, so in this first one, we see that as our x's are tending toward -3, and what we're demonstrating here is that we're tending toward -3 from the left and from the right. And we see something interesting happening with our y values. Our y values, even though there's kind of some numeric patterns going on in here, really the x's are going toward very large positive numbers as we approach from the left and very large negative numbers as we approach from the right. So if you can try to picture what's going on in the graph there, also pay attention to the fact that at -3, the function f of x is actually undefined. So to me, that tells us that we have a vertical asymptote at x equals -3. And maybe you remember now doing this very thing last year in honors pre-calculus. Now, back over here, you see some statements that kind of look like your end behavior statements, but really you can use them just as you're approaching any number. In this case, we have x approaching -3 from the left. And as the left side of the table indicates, as we approach from the left, our numbers appear to be going toward positive infinity. Now, as we approach from the right, it's still unbounded behavior, but it's toward negative infinity. So that indeed is our vertical asymptote. Now it actually said, also make a conclusion about what's happening in the equation. Remember that if you have a vertical asymptote, that is a factor in the denominator that is causing your function to be undefined at x equals -3. So we must have a factor of x plus 3 in the denominator. Okay, so the second table, we are approaching, we're approaching 2. Coming in from the left, it appears that our y values are approaching -0.4. Coming in from the right, once again, it appears our y values are approaching -0.4. Maybe it's not exactly that, but our best guess, our conjecture would be that because the function's undefined at 2, but our y's are approaching the same value of -0.4 from the left and from the right, that would be a hole in the graph at 2 and -0.4. Now, again, remember, that's not actually a point on the function. We'd literally draw a little hole there if we were graphing this. And we know that this is caused by a factor in the numerator and the denominator. In fact, it'd be a factor of x minus 2 in both the numerator and denominator that causes a hole rather than a vertical asymptote. Now, again, our statements here as x approaches 2 from the left, it appears that our y's are approaching -0.4. Same thing from the right. So our y's are consistent as we approach that target x value of 2. Now our last one here, again, I know this is familiar to you, but in this one, we're not approaching a particular x value. So something interesting is happening here. We're saying as x is going to basically positive infinity, as you see right here, so this is a true end behavior, your y's appear to be going toward 2. Again, that's a conjecture. It's our best guess. And as our x's go to negative infinity, right here, our y's again appear to be going toward 2. So if you can picture at the extreme values of x on your graph, your y's are going toward -2. So that would be a horizontal asymptote at y equals 2. Now, what that means for your equation is that, maybe you have the same degree on the top and on the bottom, but the ratio of the leading coefficients is 2. So all of this, if you remember toward the end of last year, this is kind of what we ended on last year. During our quarantine, we were working on all of this. Okay, so let's go ahead and move on because obviously we're not just doing pre-calc in here, we're doing some calculus. So there's this super important concept called a limit, and it says, and this is an informal definition, I'll explain that in just a second, but as x approaches, if f of x becomes arbitrarily close to a single number L, it's got to be a number, all right? As x approaches c from either side, then the limit of f of x as x approaches c is L. Now, of course, that sounds very wordy, but basically, we're just saying if our function f of x or our y values become super duper close, arbitrarily close, to a particular number as x approaches from either side. Now, that doesn't mean just from one side or the other. That's saying as you look at it, if from the left and from the right, it's approaching a particular number L, then the limit of f of x as x approaches c is L. All right, so and we'll write it just like this guy right here. So we know that this L is a number. It has to be a number. And I'm making a big deal about that because sometimes we see our graph approaching infinity. Infinity is not a number. That means it's not a limit if the function is approaching infinity. All right, and then also we see here that x is approaching c, and we have to keep in mind that that is from the left and the right. So if we go back to the previous slide, this one in red right here in the middle, this looks like a limit truly because we are seeing that x is getting arbitrarily close to 2 and our y's are getting very close to -0.4 coming from the left and from the right. So we could say, if I can squeeze it in here, the limits as x approaches 2 of f of x is -0.4. Now, it doesn't matter what's actually happening at 2 because the definition says nothing about, there having to be a value there. In fact, it just says it's what is happening as f of x becomes very close to c, as it approaches c from either side. In fact, I made a little statement here. The existence or non-existence of f of x at x equals c, so whether or not it's defined there or not, has no bearing on the existence of the limit as x approaches c. All right, so it could be true that the function is defined everywhere but that value of c that you're approaching, and your limit still exists at c. Okay, let's take a look at this guy right here. So it's asking you to sketch the function and then find the limit. As I said earlier, we're going to be looking at kind of a graphical representation or a graphical way of justifying, and then numeric as well. I know if I plug 1 into here that I'm going to get 0, right? I'm going to get 0 over 0. So that's not very helpful. But I also know I can manipulate this a little bit. And just from what we know from algebra 2 and pre-calculus, we get x squared plus x plus 1. all over x minus 1. All right, so we can cancel these out, and we can say that f of x is just x squared plus x plus 1. Don't know why I'm using a parenthesis there. But we have to limit our domain of that and say x cannot equal 1, okay, because then it would truly match this function up here. So if we're going to go ahead and sketch that, we just need a really rough sketch of it. We know it opens up. We know the y-intercept is at 1. We know the vertex. Where's the vertex? Negative opposite b over 2a. All right, so it's at negative 1/2, somewhere over here. And your graph is opening up. I'm not doing a very good job labeling my graph. But your vertex is, somewhere over here. Wow, that's terrible. It's going to look something like that. But this is a little bit misleading because I know that x is not allowed to equal 1. So I would maybe come over here and I would put an open circle at x equals 1. Maybe right there. Wow, that's giant. Can I move this feller? Maybe I should just use my pen to do that. So we would have an open circle right about there at positive 1. I promise my graphs will improve. But if we have, let's see, an open circle there. In fact, if I plug 1 into this guy right here, so if I find f of 1, I get 1 plus 1 plus 1, I get 3. Okay, so this whole is at 1, 3. Which means as I approach 1 from the left, and as I approach 1 from the right, even though my function's undefined right at 1, my y values are approaching 3 from both sides, so my limit is 3. Okay. All right, let's take a look at a better graph of that, much better than I had. So there's the actual graph. Here's what my numeric justification would look like, just like when you were investigating functions last year in honors pre-calc. You would make tables like this, or you would fill them out and then kind of make the conclusion. That's what you will be doing here as well. So here's your graphical justification, just the graph, showing that it approaches the hole right there at 1, 3, and then your numeric justification. Okay, so this guy right here looks quite a bit scarier, and we're going to be learning how to deal with this algebraically. But once again, here we're just estimating numerically and then verifying graphically. So we're actually going to use our graphing calculator to do that. And in fact, we're going to use our graphing calculator to fill in some values here. So if you remember, we're going to make our table of values because it's numeric. And I'm going to call this, I know it's not called anything, we'll just call it f of x. Okay, and I want to plug in some values very close to 0. So I'm going to start from negative 0.9, negative 0.99, negative 0.999, and then we've got I'm approaching 0. I'm not approaching 1. Let me back up for a second. Okay, back here. We've got negative 0.1, negative 0.01, negative 0.001. We've got 0, and then we have positive 0.001, 0.01, and 0.001. All right, so to find that, remember you have to put this function into f of x in your calculator. And then you want to make sure that the table set says ask. So if you do a second window on your graphing calculator, that's table set, and you want the independent variable to be ask. Dependent should still be auto because you want it to tell you the dependent. Then if you go second graph, you can fill in your table with those values. And we get some numbers here that I probably won't be able to fill in, but I got 1.9487, 1.995, 1.9995, error, so undefined. I've got 2.0005, 2.005, and 2.0488. Okay, so if we want to numerically estimate, again, just like in the tables we saw before, this isn't a proof that this is what the limit is. It is merely an estimate of what the limit is, because if we're just plugging in numbers, we're really just estimating. We're not proving a single thing, unfortunately. All right, so as we look at this, it appears that as we approach 0 from the left and from the right, my y values are both approaching or both getting arbitrarily close to this value of 2. So that would be our limit. Now, if you were to graph this fella, based on my last graph, maybe this isn't a good idea, but we know our domain goes from, well, it can't be anything less than -1 because we can't take the square root of a negative. But we also know that x cannot be 0 because that would give me 0 in the denominator. So your graph is, it's going to look like a square root function, but it's going to have a hole at 0. So maybe something like this. All right. And you, again, I told you were going to graph it, but it looks something about like that if you hit graph on your graphing calculator. All right, so there is that limit. Let's see where we are on time. Let's do just one more and we'll be done for this video. All right, so this guy, we've got an absolute value of x over x, and we're approaching 0. Now, in this one, I'm going to use some values that are pretty close to 0, but maybe not quite as close as we did in our last one. So I'm going to do, I don't know, let's do maybe like a -0.5, a -0.25, a -0.1. They don't have to be perfectly patterned. We've got 0, 0.25, try that again, positive 0.1, 0.25, and 0.5. All right, so the interesting thing here is that when you plug into an absolute value, it just means distance from 0, and distance is always positive. So if I put a -0.5 on top and a positive 0.5 on the bottom, so I have absolute value of -0.5 on top over -0.5 on the bottom. Well, the top is going to be positive, the bottom is going to be negative, but they have the same magnitude. So I'm going to get a -1. Well, the same thing is going to happen here. I'm going to get a positive on top with that negative on the bottom, so I'm going to get a -1. And the same thing here. I'm going to get a positive on the top and a negative on the bottom, so I'm going to get a -1. Again, this guy is undefined. When I put a positive 0.1 in, so it's going to be similar, but the top and bottom are both going to be positive. So I'm going to have +1, +1, and +1. So this is an interesting graph that I will tell you, AP, they just love this particular function for some reason. We have coming from the left, this is 1, this is -1. Coming from the left, everything is going to end up to be a -1. So we have an open circle right here. Coming from the right, it's going to be at a +1. So that means as I approach from the left and as I approach from the right, my y values are not approaching the same L, the same number. And so we say that this limit does not exist. All right, you might see sometimes the abbreviation DNE as well. Don't do that on the AP test, though. You want to write out does not exist. Okay, so there's an example of when our limit does not exist. We kind of had been hinting at that. In the next video, we'll look at more instances where our limit does not exist.